So fusion is something people have made on Earth multiple times, including recently in national laboratory settings. People might have seen the press on what's called NIF, the National Ignition Facility, and they said, look, more energy came out than we put into it, which was kind of this milestone. Can you talk a little bit about that and how that relates to the work you're doing?
At Xcimer Energy, we're pursuing laser-based inertial fusion, which is very much like the type of fusion that the National Ignition Facility has demonstrated. So inertial fusion is where you have your hydrogen fuel, size of a BB, and you use a very powerful laser and you shoot into the target system in billionths of a second. And that generates very high pressures ultimately around this fuel capsule. And that creates a huge compressive force on the hydrogen fusion fuel. It implodes and gets very hot and dense in billionths of a second, and then sparks. And if it's big enough when it sparks, it can self-heat, and you get a self-sustaining, very rapid burn and disassembly.
Sounds a little bit like a combustion engine in that you puff a fuel, spark, and you have an explosion.
The energy release in fusion is very different than in chemical explosives or chemistry. 80% of the energy comes off in the form of neutrons. They travel very, very, very fast. And they have long mean-free paths in any solid material. So you can have a blanket. In our case, we plan to use fly, the molten salt. We flow it in a waterfall, and the neutrons deposit their energy instantly over a very large volume. So you can instantly absorb that energy thermally.
And then how do you turn that into thermal energy you can use or electricity?
Fusion is just a fancy heat source. So you heat up a molten salt, in our case, flows out the chamber a bit hotter than it flows in, and then you use that to make steam, drive a standard steam turbine cycle.
Okay. And when you say molten salt, what does that mean?
It's a little bit more dense than water, and it's transparent, so it almost would look like a shower of water.
Okay, so just so that we have the entire end-to-end process straight. So I have a cylinder with liquid flowing down the sides. I shoot a pellet, jam it with two lasers, four lasers. How many source lasers?
Yeah. So we'll be shooting it with 2 laser beams.
Fire the pellet through, shoot it, fusion happens, it sprays this fluid with neutrons, which then heats up the fluid even more.
Yep.
You have some sort of heat exchanger at the bottom where you extract the heat and also the tritium in a different process. Use that heat for something useful, process heat, electricity, whatever it may be.
Yep.
And for a commercial plant, we're talking about something like 12 megajoules on target. And that is roughly the energy of a fully loaded 18-wheeler traveling at highway speeds. So just imagine, picture in your head, like a truck on the highway pulling a trailer, fully loaded, 70 miles an hour or whatever. All of the kinetic energy of that truck in a little pulse of light, a few billionths of a second long, focused on a pellet the size of a ball bearing.
Okay.
Cool. That's the scale we're talking about.
18-wheeler ramming into a pellet at a billionth of a second creates fusion.